Abhinav Kumar, who is going to talk about 24-dimensional cannonballs and magic functions.
So thanks very much for the invitation. It's very nice to be able to escape here every few days. So I'm very happy to have some kind of affiliation with Stony Brook. Let me just say at the outset that this is all based on joint work with various people, but the new work is all based on joint work with Henry Cohn, Steve Miller, Radchenko, and Maryna Viazovska. One more thing that I wanted to say was this is the first time I'm giving this talk, so there's probably going to be lots of typos. And so, excuse me for that. And if you have any questions at any point, just ask, and I'm happy to take up one of the boards and explain on the board. Okay, so let's get started. So sphere packings. So this talk is about sphere packings, specifically in a few dimensions, few magic dimensions, so to speak. So sphere packing is just defining the basic setup. Sphere packing in Euclidean space is a collection of equal-sized balls of which don't overlap, except they're allowed to touch. And there's a sort of obvious notion of density, and the question is basically how can we most efficiently pack spheres so that the density is maximized. So that's the sphere packing problem.
Density well defined.
Yeah, you can take. I mean, I said it's obvious, but you have to think about it a little bit. Yeah. So so the thing to do is you take larger and larger cubes, for instance, and you take the fraction that the intersection occupies, and you can take a lim inf, and you can define the density that way. So it's reasonably defined even for irregular packings where they might not be periodic or lattice. You can still define a notion of density.
Well, it's not a complete proof, right? Because you could have large regions that are empty.
Yeah.
These can oscillate such a way
Oh,
that
yeah.
the limit not be well defined.
I said take a lim inf. Yeah.
Then lim
inf.
But then if you change the center, it's not clear that.
I mean, if you have the assumption that there's a ball with
That's-
every square line.
Yeah, that's a valid point. Yeah. But so you can take you can take the minimum over all such centers.
Take the lim inf and assume, sure.
You can take the I was going to say you can take the minimum over all the centers, possible centers. But okay, so let me go on. So let's look at the answers to this sort of very easily stated question. So in dimension 1, this is pretty easy. Balls are just intervals, so you can get density 1. That's the long and short of it. And already in dimension 2, it starts getting a little interesting. So the obvious packing is you start playing with coins. You'll see that you can. The best way to do it is in a hexagonal arrangement. But the first proof was not until 1940 or so. And then it gets even harder. So the three-dimensional case was the original Kepler conjecture. So Kepler conjectured that the best you could do was take layers of these plane packings, take spheres, and then layer them on top of each other in an efficient way, and that's the best you could do. And one of those packings is the face-centered cubic lattice packing, or A3. There are infinitely many of the same density. Anyway, that was the Kepler conjecture, and to prove it is quite difficult. So this is
the same Kepler as in.
Yeah. So Kepler. So there's a nice story behind. I mean, so Kepler. This really was studied by Kepler's assistant Thomas Harriot, who was sort of interested in things like packing cannonballs on a ship or whatever. How do you sort of pack cannonballs efficiently? And Thomas Harriot was also very he was a big proponent of the sort of atomic theory of matter and so on, which Kepler wasn't. He managed to convince Kepler that was the way to go. Anyhow, so this is the original Kepler's conjecture, and it took several centuries to prove. And now there's a sort of this has been verified two ways, so to speak. So Hales, when he first proposed a proof, I think around 98 or 99, referees sat on it for about a year and then sort of essentially gave up refereeing the proof because it was very. I mean, He sent me much later, of course. I got a bunch of his papers in the annals, and I decided I'd read them someday. That day hasn't happened yet. Anyhow, so the referees gave up, and then the annals published the proof and said that they weren't able to fully check it, and this made Hales very mad, as you can you can imagine. He started on a project to computer verify the proof. It's called the FlySpec project, and that only got completed a few months ago. So now there's sort of two possible verifications. One is human and one is computer. So it really is true. Okay, there's no doubt about it. Anyway, so that's the layering that you take. You take one layer of the hexagonal lattice and you fill in the holes by the next layer and so on. And you see that there are two ways to put the centers. You could put them here where I've put them, the centers, or you could put them here. And so at every stage you have choices. So there are uncountably many ways to do this in 3 dimensions. They all have the same density. Those are called the Barlow packings. Here's an image from Wikipedia, sort of the lattice arrangement, the face-centered cubic. Okay.
Who was Barlow?
Barlow, that's a good question. I didn't really look into it. Yeah, I'm guessing somebody who thought about these things and realized that you could layer these things, and get infinitely many ways. But yeah. So right, as far as answers go, that was the end of the story till a few months back. So I should say we had guesses for the densest sphere packings, and well, we still have guesses for many. So in higher dimensions, I mean roughly up to 8 and dimension 24. We have some guesses in intermediate dimensions, but once the dimension gets really high, like 100 or 1,000, then you expect that the answers will be almost disordered. You can take any almost disordered. Almost meaning, so you can take an arbitrary sphere packing, and you can take that arrangement of take a large cube and throw away everything that's on the boundary, and then just tile. Right? So you can approximate the density of any of arbitrary sphere packings by periodic ones. So so that way you can show that you can approach the density, the densest arrangement by periodic packing. So in that sense, one expects that. But you expect the number of translates. Expect the number of translates in a fundamental domain for the denser sphere packings in an arbitrarily high dimension to be fairly large to grow with dimension. I mean, this is based on sort of no evidence whatsoever. So there's a little bit of evidence. Let me yeah.
Are there higher dimensional examples that are like these Barlow packings where you have a lattice?
Yeah.
But then you can also find another packing which is not periodic.
So yes. So in 9 dimensions, the current record. Sorry, up to 8 dimensions, the current records, except for the 3-dimensional Barlow case, So let me just say, so in all these dimensions, you can match the density with non-periodic, with non-lattice packings. In 9 dimensions, something curious happens. The best known are these what are called fluid diamond packings. I mean, you can decompose them into 2 cosets of a lattice, and you can translate one coset arbitrarily far without overlapping with the other one. So that's why they're fluid diamonds, so to speak. And so most of them are going to be not lattices. They're going to be 2 points per fundamental domain. And in dimension 10, something even weirder happens, which is the best known packing is called the best packing. It's not because it's known to be best, because it was discovered by Mr. Best. So Mr. Best discovered this packing from binary code, and it has 40 translates of a lattice, so 40 cosets of a lattice, and that's, nobody's beaten that with anything else so far.
Understanding this connection with the word translate and something not being true,
So a lattice packing is, you just take, a standard notion of a lattice, whereas a periodic packing would be, you would have multiple, you would put the sphere centers at, you have n points per, lattice fundamental. No, a periodic packing. So yeah. a periodic packing would have n points, some number of points per fundamental domain, and they would have. So you would not have full translation symmetry, but you would have sort of partial symmetry, so to speak. Does that make sense?
In other words, the units that are translated by the lattice group are not individual spheres, but certain collections of them.
Yeah, exactly. I mean, I could draw a picture for you if you. Let me see if I can. How do I? Can I put that one? Thanks. So here's an example. So in 2 dimensions, the obvious lattice packing is this one. I'm just drawing the centers of the spheres, but what you can do is you can drop this center and make a packing with hexagons, and that's not a lattice packing because it doesn't have. It's not equally dense as the previous one, of course, but that's what I mean by lattice packing. This has more than one. If you take a fundamental domain to be something like this, it has more than 1 point per fundamental domain.
Or to be sillier, I mean, you could put some small spheres inside that hexagon.
Yeah, you could put. Right. And you could have a smaller sphere. I mean, it could put some other point here and then just translate it and so on.
I can't understand things from examples. I need an abstract statement.
Okay. Sure.
It's okay,
though. Okay. All right. Let me go on with my talk, and I'm happy to explain this later. If I can have that back now. Okay. So anyway, so I was going to say, the dimension in which we have guesses for the densest packings mostly arise from lattices, but we did not have proofs until very recently. So okay. And this is the other thing I wanted to say. In very high dimensions, we don't expect them to be close to lattices. Okay, so this I assume everybody knows.
They're close in density to disordered packings. In other words, you can approximate. What does that mean?
No, close in character is what I meant. Yeah, not close in density. Right. We expect them to be. So we can get arbitrary. Yes. How would you like me to?
What does close mean?
I mean, you could define a distance between. You could.
Oh, there's the missing word in very large dimensions.
In very sorry. Yeah. So the English is flawed in many places. Right.
Likely to be very large dimensions, something is likely to be true.
Close. I just mean. I don't mean in. I'm sure you could try to define this in some metric way, but I just mean close as in they'll have many more points per fundamental domain. So lattice would have 1 point per fundamental domain, and I'm saying that you would have, if you want the densest packings, you would have to use periodic packings which have lots and lots of points per fundamental domain. So you couldn't. It would sort of not be as symmetrical as a lattice.
This is still making comparisons among various periodic packings. But
Yeah, I mean,
there are aperiodic packings that are better. We just don't know how to look for them.
there might be aperiodic packings which are better than in a specific dimensions. There might be an aperiodic packing which is better than any periodic packing, but you can approach its density arbitrarily closely by a periodic packing in that dimension, just by that construction I gave you, where you sort of take a large cube and tile. And you can convince yourself that you can get epsilon close for any epsilon. Okay. All right. So anyhow, let me go on. So lattice, right? So just basic definition. So I'm just mean a sort of a positive definite lattice, some discrete subgroup inside Euclidean space generated by n linearly independent vectors. And for instance, we'll say it's an integral lattice if the dot product between any two vectors is an integer. We'd say it's an even lattice if the norm of any vector is an even integer. Even implies integral, so on. So here are the sort of usual suspects. This is the most famous lattices in low dimensions, at least. So there's the integer lattice, z to the n. There's a checkerboard lattice dn, where you take all this stuff which has even coordinate sum. There's a simplex lattice, there should be a boldface Z. So you take stuff in n+1 dimensions with 0 coordinate sum, and you look at it inside that hyperplane with 0 coordinate sum. So that's the simplex lattice AN. And then there are special root lattices E6, E7, E8, which everybody knows, but let me just say. So E8 is generated by in 8 dimensions, a specific thing. You can generate it by taking D8, the checkerboard lattice in that dimension, and the all halves vector. So that's E8. And you can get E7 by just taking the orthogonal complement of a root vector of norm 2. In other words, the orthogonal complement of an A1 lying inside E8. It doesn't matter which A1 you take. They're all symmetric. And E6 you can take an orthogonal complement of A2, and you can get E6 from E8 this way. So these are the special sort of lattices up to 8 dimensions. And here's a picture which I'm sure all of you must have seen by now. This is the projection of the 240 roots of E8. I think even Congress has seen this picture. Okay.
Are you more mystified than we are?
Sorry? They might be, yeah, they might be a little more mystified than you. That's right. Okay, so, and then let me just define the Leech lattice, since that will play a role. So in dimension 24, we have the Leech lattice. It's kind of a interesting object, shows up in many different branches of math and physics. Here's sort of what I call a zero knowledge definition. It's the unique even unimodular lattice in dimension 24 without any roots. So
what is a root of a lattice?
Vector of norm 2.
Huh?
Vector of norm 2. A root of norm 2. Yeah.
With which normalization? So it's unimaginable.
So yeah, I normalize it so it's even, so it's integral in particular, and it's unimodular. So I also normalize it with that. So it has volume 1, co-volume 1. So that, I mean, that sentence tells you, I mean, characterizes the Leech lattice, but doesn't really tell you how to construct it. If you want to know how to construct it, there are many very nice constructions. Conway and Sloan have a paper called 23 constructions of the Leech lattice, starting with what are called the Niemeyer lattices in 24 dimensions. And the usual construction that people go with is starts from A1 to the 24th and uses the extended Golay code, which is a special binary code. It's a very nice code, but here's my favorite construction. So you can start with the Lorentzian sort of 26-dimensional space, R25-1, with that metric, and you can take all the vectors, all the integral vectors inside it, or all the integral plus a half vectors inside it with even coordinate sum. So that gives you the lattice 2 sub 25-1. That's an even lattice. It's got signature 25-1, and it's unimodular. And
where does the Lorentz norm come into the definition?
I mean, I haven't defined the Leech lattice yet, but you can understand this lattice as a subgroup of that with the quadratic form. I mean, lattice usually you will take z to the some power, and then you take a free abelian group with some quadratic form. That's equivalent to defining a lattice with some signature. So to define Leech, you notice there's a particular vector in here, which is 0, 1 through 24, comma 70, and it has norm 0. So it's a 0 norm vector because of that nice property, which doesn't hold for any larger value of 70. Okay, so then the Leech lattice is, so because W lies in W orthogonal, you can mod out W orthogonal by ZW, and then you get a definite positive definite lattice, which is the Leech lattice. Okay, the induced quadratic form. So anyway, that's my favorite definition. So now I've told you how to construct the Leech lattice. Let me say, yeah. So let me go back to a lattice packing. So I mean, intuitively, it's clear what we mean.
I'm sorry. Can you go back because I'm confused here. So when you take W perp, that would include perp W because
that's right. Yeah. So W perp will, yeah, exactly. So W perp will it be a 25 dimensional thing, and you mod out by 1, so you get 24 dimensional.
So you drop 2 dimensions.
That's right. Yeah. Right. Other questions? Okay, so right. So if you have a lattice, then the sort of intuitive picture is you want to put balls at the lattice vectors which are largest possible, and that largest possible is basically you take half the length of a minimal non-zero vector of the lattice. So m of lambda is going to be that minimal non-zero length, and you take half that length, and that's the best you can do, and that gives you some density for the lattice. Okay, so so you can define a lattice packing problem because the sphere packing problem is so hard. You can restrict it for lattices, and that's a little easier. And it's equivalent as sort of a classical number theoretic problem. You can rephrase it in quadratic form language, and it's equivalent to determining the Hermite constant gamma n. Okay, and so we know some more answers for that at least. So one is obvious, 2 and 3 are due to Lagrange and Gauss. Korkin and Zolotarev around 1900 or so finished off 4 and 5, and then Blichfeld in 1930s did 6, 7, and 8 in a proof that's very hard to read. And we had a proof with Henry Cohn. We had a proof around 2003, got published a few years later, that the Leech lattice is the densest lattice in 24 dimensions. We also got another proof of E8, and that was using some of the technology that I'll talk about, which is linear programming bounds. Okay. So, all right. So let me tell you what the new results are. So, the first big result is the theorem due to Maryna Viazovska that the E8 lattice packing is not just the densest lattice packing in 8 dimensions; it's the densest sphere packing in 8 dimensions. Okay, and then we shortly followed this up by proving that the Leech lattice is the densest in 24 dimensions. So that's 2 more dimensions down, and I guess you could ask, what about other dimensions like 4 dimensions? Why did you skip all the way to 8 dimensions? And we'll see some reasons why that is. But roughly, the idea is that 8 and 24 dimensions are very special. There exist these amazing lattices which roughly tell you the answer. 4 dimensions, there is a nice lattice T4 which is suspected to give you the densest sphere packing, but it's not quite as amazing as E8 or the Leech lattice. So we're still a ways off from proving anything about it. Okay. So the 2 main things that we'll use are, I'll talk a little bit about our linear programming bounds for sphere packing and modular forms. So the linear programming bounds we knew for a while. I mean, when we wrote this lattice paper, we had developed enough intuition about these things and enough numerics to understand that part. But really, the new sort of ingredient was using modular forms to write down sort of exact answers. So that's sort of the miracle in step 2. Okay. All right. So let me talk a little bit about linear programming bounds. So I'm going to normalize the Fourier transform of a nice function, let's say a Schwartz function, by that normalization, and the linear programming bounds for sphere packing, which are due to Henry Cohn and no Melkis, say the following thing. So suppose you take a Schwartz function with the following properties. So you normalize it to have value 0 and its Fourier transform also to have value to have value 1, and its Fourier transform also has value 1 at 0. Then you assume that it's non-positive for x of length at least r. Okay, so beyond that length becomes non-positive, and the Fourier transform is always non-negative, okay, for every value. So then the following surprising conclusion emerges. So there will be an ingredient in the statement which will come from this R. Okay, density of any sphere packing in n dimensions is bounded above by that number. Okay, so that's the linear programming bound. So volume of Bn is just the volume of the unit ball in n dimensions, and R/2 is the radius of the sphere packing associated.
What do you mean by the phrase linear program?
The phrase linear program is the same as the phrase linear program in computer science. So it's the following thing. So you've got some kind of object inside either Euclidean space or Hilbert space or whatever you have, which is cut out by linear constraints, linear inequalities, and you want to optimize an objective function which is also linear in the variables. That's just so, and the answer to that is a linear program. And sometimes if there are an infinitely many constraints or a continuum of constraints, you call it a convex program. I mean, in general, it would be a convex program. Linear program usually refers to finite dimensional everything, constraints, and so on and so forth. But in this case, actually, it's going to be infinite dimensional, so it's kind of an abuse of notation. It really is a convex program, but let's gloss over that. Okay, so it's called a linear programming bound. And originally, it was used for things like writing down bounds for binary codes or codes over other alphabets, or bounds for spherical codes, and bounds for combinatorial designs, things like that. So those are the sort of things that linear programs were used for in pure math, at least. So let me say, why is this a linear programming bound? And then I'll sort of sketch a part of a proof of this thing. Okay, so we can rephrase the theorem by first saying we can scale f appropriately to so that r gets replaced by 1. Okay, so I just replace f of x by f of rx. Okay, and then I need to do something to make f hat of 0 equal to 1, but I can scale. I can just multiply by a number to be able to do that.
In the dual variables, are you scaling them down, or?
Well, I haven't gotten to the linear program part yet, so I'm going to rephrase that theorem in this way, and then see that this immediately leads to a linear program. And that's why I wanted to write f hat of 0 equals 1, but not f of. I want to let f of 0. So the problem was in the previous version, r appears over here, which is not really the optimal formulation for a linear program. I mean, it doesn't look like a linear constraint. You want r to sort of show up as part of the objective function. So that's what I'm going to do. So that I replace the r by 1, and I have these things, and then the density is bounded by volume of Bn times f of 0. I might have, maybe there's sorry, there should be like, no, actually the r is not here anymore, so f of 0 has absorbed the r scaling. Okay, so I mean, this is something that you can easily work out just by the rescaling is just f of x goes to f of rx, and then multiplied by a constant, probably like r to the minus n or something, which will make this work. Okay, so now all these constraints, whatever f is, these are linear constraints, and this objective function is also linear. The variable, so to speak, or your vector is f. That it's linear in f. F hat is of course a linear transformation. So that's why this is a linear convex program. Okay, well, you have an infinity of constraints, so technically it's not a finite dimensional thing. So let me sort of indicate what the proof looks like. The proof is actually ridiculously simple. So let me just show it to you for lattices, and then what you do is you show it for periodic packings, and and then by that periodic to a periodic argument, you can get it for arbitrary packings. So okay, so let's take a lattice, and we've scaled it. Suppose that the minimal non-zero vector length is 1. Okay, so I'm going to write down a bound on the density of this lattice. So let's apply Poisson summation. So f is my given function which has those properties in the previous page, and so Poisson summation for lambda tells me that the sum of f over all the points of the lattice is related to the sum of f hat over all the points of the dual lattice by this factor, the volume of the fundamental domain. Okay, and so what do we know? We know that the left hand side is at most f of 0, because I assume that f was non-positive as soon as x was more than 1 in length, and I'm assuming the lattice minimal vector length is 1, so all the vectors except the 0 vector have length at least 1. So all the values therefore are non-positive. So this side, whatever it is bounded by f of 0, and the right hand side, because f hat is non-negative, is bounded by f hat well, I should say 1 over co-volume times f hat of 0. Okay, f hat of 0, and f hat of 0 I normalize to be 1. So this just gives me the inequality that 1 over the volume of the fundamental domain of the lattice is less than equal to f of 0, and then I multiply it by the volume of the unit ball, and that tells me that the density is at most that much. Okay, so it's kind of a one-line proof. I might have fudged some factors of 1/2, but you know, that's what happens when you rewrite slides. Okay. Any questions about this proof? So the proof for periodic things is not much more.
Yes, satisfying those conditions.
Right. So if you can find me an f with those conditions, then I can give you a bound, namely this volume of Bn times f of 0. Okay. And the game is now to find the f that gives you the best possible bound. That's your linear programming game. So I just wanted to make a few remarks on how we use this thing. So first of all, we can assume that f is radial. It's radially symmetric and only a function of the norm of f, the norm of x, and you can sort of see this from the form of the theorem. But anyway, you can sort of integrate over the sphere, and you can see this. So what do we do in practice? So when we're trying to find the best possible bound, we experiment as follows. You take f to be, you want f to be a nice Schwartz function. So what you take is you take some combination of polynomial times Gaussians. Okay, so my polynomial is going to be sum of Ci Li, where Li are the Laguerre polynomials, and these have the nice property that Li has, if you Fourier transform Li, you get -1 to the I times Li. So it's an eigenfunction for the Fourier transform. Half of them are even, half of them are odd. And this, because you're multiplying polynomial times the Gaussian, you already have the nice decay properties that you want. You can take, and you can easily write down f hat now. It just involves plugging in a -1 to the I here, and then you can write down all the inequalities, and then you can, you know, in practice you have to sort of, because there is a continuum of inequalities, you have to take a bunch of approximations and so on and so forth. But you can actually get reasonable bounds this way. So we did. And what happens is you get a bound. You can get a bound in any dimension that you care about low enough. You can run the linear program. You can get a reasonable bound. I'll show you what that graph of upper bounds looks like. But the miraculous thing is in 8 and 24, you can get bounds which are amazingly close to the lower bound that comes from actually exhibiting a lattice. Okay, the E8 or the Leech lattice. So, so here's a plot of log of the density versus dimension, and this blue curve comes from the best packing known. So, and the upper bounds, well, there are a couple of upper bounds plotted. This is the sort of one of the easier. The Rogers upper bound is an easy upper bound you can write, and the sort of improvement, the next best thing, you know, the current record would be the sort of linear programming bound of Cohn and Elkies. And you see that there are at least two places where they seem to almost touch, namely 8 dimensions and 24 dimensions. Sorry, the numbers are kind of small, but those are the places where these seem to meet, and they actually also meet in 2 dimensions, but that one's an easy case anyway. So what happens in those dimensions? You can get very close to the density of the E8 or the Leech lattice. In fact, you can get, you know, an error of like 10 to the minus 30. You know, I mean, this is what we did something like 14 years ago. Now you could get, you know, much higher precision. I'll talk about that in a minute. But here's sort of the kind of function that you want. If you want that you want to plug into your linear programming bound, if you want it to match the density of the lattice, then if you go back and look at the proof of the theorem, you see that what you need for equality to hold is that I only use the value of f. What did I use? I said that f is non-positive at all the vector lengths of the lattice, and f hat is non-negative at all the non-zero vector lengths. So for equality to hold, it better be, both those things had better be 0. So f has to vanish at all the non-zero vector lengths, and f hat has to vanish at all, also at all the non-zero vector lengths, and there have to be some sign properties. So this is what f is supposed to look like. So R0 should be sort of the smallest vector length of the lattice. You want it to have a single root at R0, and then you want it to have double roots at, stay negative after that, have double roots at all the other lattice vector lengths. Okay, and for the E8, what are the lattice vector lengths? So the norms are all the even integers for E8, and for Leech they're all the even integers except for 2 because it has no roots. So this is what you want the picture to look like, and the question is, how do you make such a function such that f looks like this and f hat looks like this? So f hat has to be non-negative, but it also has to have double zeros everywhere. So that's the basic problem, and at least if you restrict yourself to 8 and 24 dimensions, which is the thing that we were most interested in doing, so you can get very close in the
less than 0 for small r.
Sorry?
The function was supposed to be less than 0.
Oh no, it's supposed to be less than 0 for r bigger than something. Let me go back to. Sorry. Yeah. So 0 less than 0 for r bigger, x bigger than r. Okay. So right. So here's what we did numerically when we showed that it was the densest among lattices. It was enough to get sufficiently high precision, and so we had to use. Well, we wanted everything not to depend on floating point calculation. So we did everything with integers eventually. We had a polynomial. We had 200 forced double roots, so we needed a polynomial of about 4 times that degree, so 803, and lots and lots of precision to get that. So, and we got an upper bound of something like that. And since then, there's been more numerical improvements by Henry and Steve, right? But that doesn't answer the question of how exactly do you solve the problem outright. How do you write down the exact functions which will solve the problem, which clearly there must be a solution. If there's something that's this close, then you have to take the leap of faith and believe that, yes, there must be something that does the job. So we were stuck for a long time. We thought of various things, but didn't quite make progress. And then there was this amazing result that was posted mid-March. So Maryna Viazovska posted, preprint to the archive, just solving this. She found the magic function f. Okay, I'll tell you where it comes from. It comes from modular forms, so to speak. But Maryna. Okay, so I am sure most of you know about modular forms, but I'll just sort of briefly go over what these things are. So roughly, there's this complex valued function in the upper half plane with lots and lots of symmetries. So specifically, you take all the invertible matrices, which are integer matrices of determinant 1, and this is sort of a picture of actually fundamental domains for all the invertible matrices, not just determinant 1. So you add 1, the diagonal matrix 1, 0, 0, minus 1. If you combine a black and a white region, like this and this, you get the normal fundamental domain that you see. Okay, so if you combine any black and any white region, you will get this is Dedekind's famous tessellation of the upper half plane. And again, take the quotient, that's some orbifold, but you can make it into an algebraic curve. CP1 minus a point, that point is the cusp at infinity. And if you go back to the upper half plane, you get infinity and all the rational numbers. And in general, you work with not just the full modular group, but some congruent subgroup of it. So everything in SL2Z, which is which is congruent to 1 mod n for some n. So you take a subgroup that contains such a group. Okay, and if you again quotient out by that, you get some complex algebraic curve. It's very fundamental in number theory. You can compactify it by adding finitely many cusps. There are only finitely many quotients of the rational numbers plus infinity by that subgroup. There's a formula for the genus. Yeah, I mean rough. That's a good question. I don't know. I don't remember actually. I don't remember if it grows linearly. Yes, it's an exercise in Shimura actually. Yeah, I don't know if anybody remembers off the top of their head how the genius goes. Okay, so right, so the definition of modular form. So that was the action of SL2Z on the upper half plane, and so there are two conditions you need to satisfy for a holomorphic function from the upper half plane to be a modular form. So namely, it has to have that transformation property. So you say something is weight k if transforms like that for all matrices in SL2Z of that form. Okay, so then the second condition uses the fact that since 1n01 it contains it's a congruent subgroup, so it has to contain some such element, and that means that it's in, if you apply that to the vector z, you get z plus n. So then you can write it as a function of e to the 2 pi I z over n, q to the 1 over n. And so the second condition says that near infinity there's some kind of power series expansion. So this is the growth condition on the modular form. Okay, so there are two conditions necessary. One is the transformation. One is the growth condition. And in general, this is for SL2Z. In general, you need such a growth condition for all the cusps. And I wrote n bigger than or equal to 0, so it's a genuine power series. If you only have a Lorentz series, so you have some negative powers, then you say it's a weakly holomorphic modular form. These will also come up. So some examples. So the first way to get a modular form is just take some nice reasonable quantity and symmetrize it by the group. And so if you just take 1 over sort of the cz plus d to the k and you symmetrize that, this is what you get. This is the Eisenstein series. If you make the constant term 1 and you expand you write down as q expansion, then you get that. Okay, let me just say for k greater than or equal to 4, there's absolute convergence and uniform on compact subsets and all that nice stuff. So you get a non-zero modular form of weight k, and you can check the invariance property immediately. And so these are the Eisenstein series, and here are the normalized versions, so E4 and E6. These generate the algebra of modular forms for the full modular group. You have E10, which turns out to be E4 times E6, and so on and so forth. Here's another nice one. So E4 cubed minus E6 squared makes the constant term go away. You divide by 1728, and you get something which is what's called a cusp form. And this is the product. There's a very nice product formula for it. Yeah, you can write it in this nice way. This is a modular discriminant. It's a weight 12 modular form. So another source of modular forms is we use an integral lattice and you take its theta function. That's going to give you a modular form. So it's just a generating function for the norms of the vectors. So you sum this q was e to the 2 pi I z, and you just sum q to the norm of the vector over 2 over all the vectors. Okay, so it's basically counts how many vectors there are of norm n for every n. And this is going to be a modular form for some congruent subgroup. Here's the sort of neat fact. If you take the theta function of the lattice E8, you get the modular form E4. So there are also classical theta functions. These are probably the oldest modular forms studied. The simplest one is theta 0, 0. This is the theta function of the lattice Z. Just q to the n squared, sum of q to the n squared over 2. And if you hit that with, so this thing is a modular form for not of all of SL2Z, but for the congruent subgroup for 2. So everything that's congruent to the identity modulo 2. And if you hit it with the remaining elements of SL2Z, you get a few other modular forms, of which these are 2. So theta 0, 1, you just have a minus 1 to the n, and theta 1, 0, you have is a translate by a half. Okay, and these are very well studied old classical modular forms, the thetas, and these are weight 1/2 modular forms. So if you take the fourth powers, you get weight 2 modular forms, and these satisfy the nice property that the first one to the fourth power is the second one to the fourth power plus the third one to the fourth power. So equals v plus w. Okay. So I should get to how do you actually use these modular forms. So usually the construction of number theoretic significance with modular forms. You take a modular form and you take its Mellin transform and you get an L function, and these things are, you know, all over number theory and very important and so on. So we're going to take a slightly different transform of the modular form and produce the functions that we need. Okay, so remember the goal is to produce these function f and f hat, and the way we'll do it is we'll write the even part of f and the odd part of f, and they're going to be separate constructions for those two objects. They're going to be slightly different, but both will use sort of an integral of a modular form. Okay. All right. So before I tell you what the construction is, we need one more extension. So I've talked about modular forms. I've talked about weakly holomorphic modular forms, which are not holomorphic but may have poles at the cusps. And then you need quasi-modular forms. So what happens if you take k equals 2 in that construction? You don't get absolute convergence, but you can write a specific arrangement of that double sum, and that gives you the Eisenstein series E2, which is also very useful in number theory. So this guy is not a genuine modular form, because if you apply the matrix 0, -1, 1, 0, which is an SL2Z, you don't get the obvious transformation property, but you get an error term, so to speak. But nevertheless, it's extremely useful. And so the algebra that it generates with the standard modular forms are called the algebra of quasi-modular forms. And another way to think about it is, if you differentiate a modular form, what do you get? So if you differentiate E4, it will give rise to E4 times E2 plus some E6 with some coefficients and so on. So this is all that we need for a construction. So let me now describe how you make these eigenfunctions for the Fourier transform. So take this very nice simple function, E4 times E2 minus E6, square it, divide by delta. Okay, so this E4 times E2 and E6 have weight 6, so the numerator has weight 12 and the denominator also has weight 12. So whatever this is, it's a quasi-modular form of weight 0, and it's got a cusp. It's got a pole at the cusp infinity because of delta. So it's a weakly holomorphic quasi-modular form, weight 0, for all of SL2Z. Okay, and then you do the following thing. You do the following Laplace transform like operation to it. So take phi 0 of -1 over z, multiply by z squared, and then this is like the previous thing that I did. So you multiply by e to the pi I r squared z dz, and then you just integrate z going from 0 to I infinity, and you can just restrict to the imaginary axis. So you can plug in z equals it, and you get some expression that you need to integrate. So this, whatever it is, it's going to be some function of r. Okay, and I multiply it by this object 4 sine squared of pi r squared over 2. So sine of pi r squared over 2 is going to have zeros at all the square roots of the even integers, and so square is going to have double zeros at all the square roots of the even integers, but you're going to get a pole at the square root of 2 from that integral. So it's going to make it a single pole, which is the kind of thing we're interested in. We want a single pole at the square root of 2, and we want a double pole everywhere else. Okay, so here's sort of what happens. If you write down the integrand, then you get that as t goes to infinity, it looks like e to the 2 pi t, and because you have e to the minus pi r squared t also multiplying it, you integrate it out, you get a dominant, you get the pole looks like pi r squared minus 2. So it's got the pole that you want, and it makes, when you multiply it by the sine squared, it makes it a single zero. So what was the need for quasi-modular forms? That's the key thing which you use to show that it's an even eigenfunction. Okay, I'm not going to go through the proof because it's a little, it takes a page or two and doesn't really make sense in a talk, but this is very straightforward. You can see it in Maryna's paper. But roughly the idea is that when you Fourier transform with respect to r, remember that you just have a z is it, so this is e to the minus pi t r squared. A Gaussian Fourier transform just takes the pi t and makes it into pi over t. So it roughly just replaces z by -1 over z, And then you use this is an element of SL2Z, so you use transformation properties of this quasi-modular weakly holomorphic form, and you see that it's an even eigenfunction. Okay. So that's the even eigenfunction. Here's the odd one. Here you take a genuine modular form, but for a congruent subgroup. So I defined U, V, and W to be the fourth powers of the thetas. They're these modular forms of weight 2. So here the numerator has weight 5 times 2, so 10, and the denominator has a delta, so you get net weight minus 2. And again, you just basically integrate and do the same trick. And you get again the same sort of property. You get a single pole and you get a double pole at all the other ones. Okay. So now all that remains is to take, so you have an even, and again you use the modular form properties to show that this is an odd eigenfunction. So if you hit it with a Fourier transform, it goes to negative of itself. So now you just take an appropriate linear combination. You want because you want f hat to have a double pole, not just a single pole at that point. If you figure out what the linear combination is, it makes you get the double pole, gets rid of that single pole, then you're okay. And then you get the double zero that you want for f hat. And then you have to verify various things, that you don't have extra roots and so on, but you can do that. So at this point, that checking requires a computer assisted proof, but it's no floating points and it's fairly rigorous, hopefully. So that was Maryna's proof of the optimality of E8, and it's kind of amazing because all it uses is that you have to write down, all you need to know is these two functions, and then you're set. The rest is like an exercise. Anyway, so then the proof of we proved that Leech is up. That was the proof for the E8 lattice. And for Leech, it's similar. I'm not going to go through all the details. It's more complicated. I mean, the key thing, if you try to think about, how do you find these things, is what you do is you look in an appropriate space of modular forms. The transformation property, which says it's an even or odd eigenfunction, leads you naturally to some space of modular forms. If you impose the fact that it has to be given by this kind of integral. And so you get a finite dimensional space of modular forms, and if you have enough numerical data, you can just match it, and you can figure out, I mean, it's a finite dimensional space, so you can just figure out what coefficients you need. So you have to do a little bit of that. I mean, I'm not saying that the 24-dimensional case is immediate, but roughly along the same lines, and checking it also is a little more complicated. So in general, so this is great that you can get 8 and 24 exactly, but what do you do in general? So you don't expect to get sharp bounds, because remember that graph only meets at those 2 points. So we don't really expect that we'll get something great, but we should be able to get much better upper bounds than the current record. So that's something we're exploring, but we're not there yet. Something that was much more immediate that we've worked on, we're almost done with, is generalizing sphere packing to energy minimization. So the question is the following: instead of looking at sphere packings, what you do is you look at you give a potential function or a repelling force between any 2 points, and you don't let them go off to infinity. So you don't want to let them escape off to infinity. If you put a repelling force between any 2 points, the natural inclination is they'll go off to infinity. But so you impose the condition that there has to be 1 point per unit volume. So you fix the point density. So given those constraints, given that constraint that the volume fraction is fixed, what's the minimizer? And that's a problem that in 2 or 3 dimensions, physicists really want to know the answer to. In high dimensions, it's a massive generalization of the sphere packing problem. So the sphere packing problem is essentially the limit. If you take a 1 over r to some power, one inverse power law of potential function, and you let the power go to infinity, you get the sphere packing problem. So we had conjectured, Henry and I had conjectured that E8, the Leech lattice, and the hexagonal lattice in 2 dimensions, these are universally optimal. So any Gaussian function, and in particular any inverse power law, they would optimize for this sort of situation. And we're pretty much almost done with the proof for E8, and hopefully in another couple of months we'll have finished the Leech lattice as well. So that's the state of affairs for for sphere packing and energy minimization so far. I'll just leave you with some references. So that's Maryna's original paper. Then there's our paper, and there was a expository paper which I'm not sure where it's appearing. I think in some European journal, which is about our work. Thanks a lot. Questions?
Are there lattices like the E8 and the Leech lattice that skip the first few positive values for Q of X?
So there are.
And hit all the rest after some point? All the other even ones?
Yeah, there are. I mean, for one thing, you could take the Leech lattice and you could just direct sum it with anything, or E8 and you direct sum it with anything. Because E8 already covers everything, you will get all the even integers. You see what I mean? So if I take if you're just looking at the norms, then the norm for the set of norms for lambda plus lambda prime will strictly contain, I mean, it will be a sum for lambda and lambda prime. So you will get lots and lots of such lattices. But I think the question that maybe you wanted to ask was, are there other cool lattices like like the E8 and Leech lattices? So there are. I mean, there are these even unimodular lattices, and there's a condition that you can impose, which is that you want it to be even and unimodular, but you also wanted to skip as many values as possible at the beginning. And they're what are called perfect lattices, and they're known in a few dimensions, but we don't expect. So I think that the latest one to be discovered was dimension 72. That was an open problem for a long time, and there was one found in 2012 or so. But again, for those ones, we don't necessarily expect some kind of miraculous proof like this, because the upper bounds are kind of still far off. Your question?
I was hoping you were going to say that this magic function was related to the potential function for some mushy sphere packing problem.
Yeah,
like,
yeah. I mean, this
like
is
you mentioned.
right.
And
so this mushy sphere packing problem is the sort of energy minimization issue. So your sphere is allowed to get closer than, that minimal distance, but they pay a price because the energy is going to go up. Right. I mean, if you can solve that universal optimality problem, then you can certainly solve sphere packing. But that problem is much harder in general. It's sort of a miracle of sorts that we can, we can conjecture and possibly prove that it works in 8 and 24 dimensions. I mean, it's you don't expect that to hold in any other dimension except 2, 8, and 24. So that's.
Right, you combine two different complicated areas.